Welcome back, grade 10s. In today's lesson, we are going to complete chemical bonding. Now, we've already looked at Lewis dot diagrams for covalent bonds. We then went on to look at ionic bonds and Lewis dot diagrams for ionic bonds. We're not finished discussing ionic bonds though. So, if you recall this periodic table with all the information on it, what we're really interested in when it comes to covalent bonds is the number of valence electrons. Because remember that in the case of covalent bonds, we need to make sure that we have 2 electrons around hydrogen atom and 8 electrons surrounding any other atom. And those represent the valence electrons. And based on the position of the element on the periodic table, you can identify the number of valence electrons. Now, when it comes to the valency, well, the valency is what we use for ionic bonds. So we know the valency of all the S block and P block elements, again, based on their position on the periodic table. Now, what about D block elements? If we want to figure out what type of compound is made, say, between iron and sulfur, or nickel and oxygen, well, we don't have the ability to work out the valency of those elements based on their position on the periodic table. And over and above that, there are some anions and cations that come in the form of compounds. So let's continue with ionic bonds. In order to be able to work out the chemical formula of ionic compounds, we need to be aware of the valency of all these elements over here based on the periodic table, but that's easy. We also need to be aware of the valency of some other common anions and cations that we cannot derive from the periodic table. So again, we can identify the chemical formula of ions of many elements based on their position on the periodic table, but there are other common anions and cations that are either in the D block or they exist as ionic molecules. The names and formulas, including the charges, need to be memorized. Now remember that in science, there is not a lot that you need to memorize. You need to memorize definitions, and this table of common cations and anions you do need to memorize. So here we've mostly got D block elements. Note that we've got lead and 2 tin ions. Those are in the same column as carbon and silicon. Those are the potential ions that these 2 elements make. When it comes to hydride, remember that hydrogen can make the H plus ion if it loses an electron, but if it gains an electron, then it forms hydride, which is H minus. Now, all the rest we can see are ionic compounds, meaning that there are 2 different types of atoms that are chemically bonded to each other. And what we need to realize is, for example, in the case of NH4, which is ammonium, it's nitrogen and 4 hydrogen atoms attached to it, and the entire ionic compound has a deficit of 1 electron. If we consider carbonate, it's a carbon atom with 3 oxygen atoms attached to it. And the entire ionic compound has an excess of 2 electrons that it is carrying. So here's the ammonium ionic compound. It is NH4, and the whole compound has a plus sign, meaning that it has a deficit of 1 electron. And over here, we've got CO3. So it's a carbon atom with 3 oxygen atoms attached to it. And the whole compound has an excess of 2 electrons. What you need to realize is that the N and the 4 hydrogens can never be separated from each other. The carbon and its 3 oxygens can never be separated from each other. They're a family group. Now, when it comes to bonding ionic compounds, let's first look at a similar example with single elements. Like if I wanted to take lithium plus and bond it to O2 minus, well, we already learned, and we should by now be familiar with the fact that this will form the compound Li2O, because I need 2 lithium atoms to give away 2 electrons for oxygen to be able to gain 2 electrons. Now, oxygen can only gain 2, and lithium can only give up 1. So we need 2 lithium atoms to balance out 1 oxygen atom in the lithium oxide compound. It looks a lot more confusing when we deal with ionic compounds like this one, but we've got to treat it in exactly the same way as if the NH4 was a single atom with a plus, just like lithium with a plus. It's the same as saying CO3 2 minus and O 2 minus. So we can treat this almost like it's a single atom, but of course it's not. So again, if we use our crossing method, which we learned in the section on the periodic table, we need 2 of these to balance out 1 of these. So in the same way that Li plus and O2 minus will make Li2O, NH4 plus and CO3 2 minus will make NH4 2 CO3. Now, the reason that we put the NH4 in brackets is because we need 2 family groups. We don't put lithium in brackets because it's a single element anyway. And we don't put the CO3 in brackets because it's only 1 family of CO3 that's required. Again, this table's not provided on a formula sheet. We need to know these chemical formulas off by heart. So based on the periodic table and the table of ions, we may provide the chemical formulas of ionic compounds, and we learned how to do this in the section on the periodic table. If you need to go back and recap that, we used the crossing method, but we also need to be able to provide a balanced ionic equation for the formation of ionic compounds, and I'm going to show you what that means. So, for example, if I ask for the balanced ionic equation showing the formation of ammonium nitrate, so what we know is what the ammonium ion looks like, and we know what the nitrate ion looks like, and then we need to make sure that we balance out the charges. So the ammonium ion is NH4 plus, and the nitrate ion is NO3 minus. So NH4 wants to give away an electron and NO3 wants to gain an electron. So it takes 1 ammonium ion and 1 nitrate ion to balance out the charges. So we can say that 1 NH4 plus and 1 NO3 minus makes 1 NH4 NO3. And this is the chemical formula for ammonium nitrate. Let's look at lead-2 carbonate. So the lead ion, lead-2, is Pb2 plus, and the carbonate ion is CO3 2 minus. So this guy wants to give away 2 electrons, and this guy wants to gain 2 electrons. So it takes 1 ion of lead to balance out the charge of 1 ion of carbonate. So 1 Pb2 plus and 1 CO3 2 minus makes 1 PbCO3. Let's look at sodium nitrate. The sodium ion is Na plus. We can derive that from the first column of the periodic table. The nitrate ion is NO3 minus. Again, we have a sodium ion that wants to give away an electron and a nitrate ion that wants to gain an electron. It takes one sodium ion and one nitrate ion to balance out the charges. So Na plus and NO3 minus makes NaNO3 in a 1:1:1 ratio. Sodium nitrite, well, the nitrite ion is NO2 minus. I specifically included this so that we don't forget the difference between nitrate and nitrite. So in this case, again, it takes one Na plus to one NO2 minus to balance out these charges. So one Na plus plus one NO2 minus makes one NaNO2. And let's be careful with sodium nitride. The nitride ion is just the ion that nitrogen makes, and based on the column where nitrogen exists on the periodic table, the nitride ion is simply N3 minus. So this comes from the periodic table, whereas nitrate and nitrite come from the table of ions. Now, in this case, we've got an Na plus and we've got an N3 minus. So sodium wants to give away one electron, but nitrogen needs to gain 3 electrons. So we can't just have one sodium atom to try balance out a nitride ion. So in this case, we need 3 of these ions in order to balance out the charge of one ion of nitride. So in terms of a balanced ionic equation, we would show 3 Na plus plus N3 minus makes Na3N. Again, using the crossing method, we would know to put the 3 as a subscript next to the Na, and a 1, which is an invisible subscript, next to the nitrogen. But here there's an added level of complexity. If I ask you for a balanced ionic equation, I specifically want to see that it takes 3 sodium ions to balance out one nitride ion. Let's look at tin 2 phosphate. So the tin 2 ion is Sn2 plus, and the phosphate ion is PO4 3 minus. Now that means that tin wants to give away 2 electrons and phosphate wants to gain 3. Now, using the crossing method, we would know to put the 3 as a subscript next to the Sn and the 2 as a subscript next to the PO4. Remember that because the PO4 is a family unit, then the PO4 would have to go in brackets with a 2 outside of the bracket, indicating 2 PO4 family units. But it's a little bit different when I ask you to balance it for me. So yes, the chemical formula of tin 2 phosphate would be SN3PO42. But specifically, I need you to show me that it takes 3 of these guys to balance out 2 of these guys. And that's because the lowest common factor here is going to be 6. So 3 SN2 pluses and 2 PO4 3 minuses are needed in order to make 1 SN3 PO4 2. This subscripted number gives you an indication of the number that's going to go on the left in the balanced ionic equation on the reactant side. This subscripted 2 also gives you an indication of the 2 that's going to go on the left over here. Let's take a look at iron 3 chromate. The iron is Fe3 plus, and the chromate ion is CrO4 2 minus. So that means that there is a Cr atom with 4 oxygen atoms surrounding it, and the whole ionic compound has 2 extra electrons on it, whereas an iron 3 ion wants to give away 3 electrons. It therefore means that we need 2 of these 3 pluses, which in total will make 6 plus, to balance out 3 of these 2 minuses, which in total will make 6 minus. So the balanced ionic equation is 2Fe3 plus 3 CrO42 minus makes Fe2 CrO4 in brackets and 3 outside the bracket. Using our crossing method, we would know that the 2 becomes subscripted next to the ion and that the 3 becomes subscripted next to the chromate ion. Just remember that you've got to put the whole chromate ion in a bracket because it means that we need 3 of these ions in total. They can't be separated, they're a family unit. So in terms of creating or in terms of figuring out the ionic compound that's going to form from ion 3 chromate, you should be able to do that with relative ease by now. But knowing to put this 2 to the left and this 3 to the left in order to balance your ionic equation, that's an added level of complexity that I've introduced here. So for the rest of this lesson, we are just going to practice. And I'd like you to now pause the video and work through the workbook and try to answer the questions in terms of completing your ionic compounds. And when you're done, you can unpause the video and look at the answers with me. So here we've got a table where we've got some positive ions. Remember, the positive ion always comes first. And then we've got negative ions. So in this case, I want to know what compound forms from K plus and OH minus. So that's simply KOH. Next is the ionic compound that will form between K plus and O2 minus. We need 2 K pluses to balance out 1 O2 minus. So it would be K2O. Over here, we've got a single plus, and over here, we've got a single minus. So they balance in a 1-to-1 ratio to form KNO3. And over here, again, we've got a plus, but in this case, we've got 3 minuses. So we need 3 of these to balance out 1 of these. So we get K3PO4. Let's move on to the next column. So here we're forming compounds with a calcium ion, which is Ca2 plus. I have a charge of 2 plus here and a single minus over here, which means that I'm going to need 2 of these. But because this is an ionic compound, I'm going to have to place it in a bracket because it's a family unit. It cannot be separated. So I would end up with CaOH2. Over here, I've got a 2 plus and a 2 minus. Therefore, they will get together in a 1-to-1 ratio, forming CaO. 2 plus and a single minus. So I need 2 of these nitrate ions in order to balance out 1 calcium ion. Because NO3 is a family group, the nitrogen and its 3 oxygens cannot be separated from each other. They're going to go in a bracket with a 2 indicated outside the bracket. So it's CaNO3 2. Again, we've got a 2 plus here, and we've got a 3 minus over here. So we need 2 of these to balance out 3 of these. Positive ion always comes first. So it is Ca3PO4 2. Let's take a look at the ammonium ion. Ammonium hydroxide, 1-to-1 ratio, forms NH4OH. Here I've got a single plus, and here I've got 2 minuses. So I need 2 of these to balance out 1 of these. Hence the NH4 will go in a bracket with a 2 outside the bracket. It will be NH42O. NH4 plus and NO3 minus simply come together in a 1-to-1 ratio. forming NH4NO3, and NH4 plus with PO4 3-, I need 3 pluses to balance out this single 3-, which means I'm going to need 3 of these guys. It's going to be NH4 3 PO4. This question is a little bit more complicated in that I've asked for the balanced ionic equation. Again, it's easy enough for you to work out the ions and the chemical formula of the ionic compound, but there's an added level of complexity in providing the balanced ionic equation, meaning that you show me the number of ions needed of your positive ion and your negative ion on the reactant side of the equation. Let's take a look at the first one. The first one is iron 2 chromate. So first thing we need to do is figure out what the iron 2 ion is and what the chromate ion is. So it's Fe2 plus and CrO4 2-. Then the next thing we need to do is figure out the chemical formula of the product. Now, because iron gives away 2 electrons and chromate wants to gain 2 electrons, they come together in a 1-to-1 ratio. So it takes 1 iron 2 and 1 chromate to make 1 iron 2 chromate. Let's look at sodium oxide. So the sodium ion is Na plus and the oxide ion is O2 minus. That is going to create Na2O. But if we now go back to our ionic equation and try to balance it, we can see that we need 2 Na pluses in order to balance out an O2 minus. So if we can figure out that this is the chemical formula of sodium oxide, Na2O, this 2 gives us an indication that we need to put a 2 on the left of the balanced ionic equation on the reactant side. Let's look at barium sulfate. Barium is in column 2, so it's Ba2 plus, and the sulfate ion is SO4 2-. And this is nice and easy because there's a 2 plus and a 2 minus. They balance each other out in a 1-to-1 ratio. So 1 Ba2 plus and 1 SO4 2- will make 1 BaSO4. Aluminium chloride. The aluminium ion is Al3 plus. The chloride ion is Cl minus. Now, that is why if we use the crossing method, we would get Al1, which we ignore the 1, Cl3. So the compound aluminium chloride is AlCl3. But if we now go back to this ionic equation and we want to make it balanced, we need 3 Cl minuses to balance out 1 Al3 plus. Magnesium phosphate. The magnesium ion is Mg2 plus, and the phosphate ion is PO4 3-. So our compound is going to be Mg3 PO4 in brackets 2. Now we can use these subscripted numbers to give us an indication of what will go on the left-hand side. On the reactant side, we need 3 magnesium ions in order to form 2 phosphate ions. So on the reactant side, the numbers are going to go on the left, and on the product side, the numbers are going to be subscripted. Tin 2 bromide. Tin 2 is Sn2 plus, and bromide is Br minus. So we need 2 bromide ions to balance out 1 tin 2 ion, resulting in SnBr2. Manganese 2 phosphide. Manganese is not magnesium. Manganese is its own element. It is Mn as opposed to magnesium, which is Mg. The manganese 2 ion is Mn2 plus. The phosphide ion can be derived from the periodic table. We can see Where phosphorus lies, the column that it's at is in the same column as nitrogen, and those elements form the 3- ion. Therefore, the compound will be Mn3P2 if we had to use the crossing method. And that means that we need 3 Mn2 pluses in order to balance out 2 P3 minuses. If you go 3 times 2, you'll get 6. And if you go 2 times 3, you'll also get 6. So you need 6 pluses, 6 electrons to be given away in order to balance out 6 minuses, which are the 6 electrons that need to be received. Iron 2 sulfate. Fe2 plus and SO4 2 minus. This is an easy example because the charges balance themselves, so they get together in a 1-to-1 ratio to make FeSO4. Zinc chloride. The zinc ion is Zn2 plus. The chloride ion is Cl minus. So we need 2 Cl minuses to balance out 1 Zn2 plus, forming ZnCl2. Sodium carbonate. The sodium ion is Na plus, and the carbonate ion is CO3 2 minus. So I need 2 pluses in order to balance out a 2 minus. So I need 2 sodium ions to balance out 1 carbonate ion, hence Na2CO3. Copper 2 nitrate. The copper ion is Cu2 plus, and the nitrate ion is NO3 minus. So that results in the formation of CuNO3 2, because I need 2 NO3 minuses in order to balance out 1 Cu2 plus. Potassium permanganate. The potassium ion is K plus, and the permanganate ion is MnO4 minus. We need to balance these charges in a 1-to-1 ratio, resulting in KMnO4. Magnesium permanganate. The magnesium ion wants to give away 2 electrons, whereas the permanganate ion wants to gain 1. So we need 2 permanganate ions in order to balance out 1 magnesium ion, resulting in MgMnO4 2. Again, the 2 lies outside the bracket because MnO4 is a family group and we need 2 of this family to bond with 1 magnesium. Manganese IV dichromate, that is Mn4 plus. Now, Mn4 plus wants to give away 4 electrons, and the dichromate ion is Cr2O7 2 minus, so it wants to gain 2 electrons. Now remember, if you're going to use the crossing method, we know that we're going to result in Mn2, then Cr2O7 4, but we need to find the lowest ratio, which means that the Mn2 and the Cr2O7 4 become a 1 and a 2. So that was one of the issues with the crossing method, where it doesn't always serve us and we can't forget to find the lowest ratio. So now that we've figured out that the compound manganese dichromate is MnCr2O7 2, well, that means that we need 1 manganese to 2 dichromate ions in order to balance out. Manganese 2 hydrogen carbonate, that's Mn2 plus, and the hydrogen carbonate ion is HCO3 minus. I need 2 of these to balance out 1 of these, hence it's MnHCO3 in brackets with a 2 outside the bracket. And finally, let's look at chromium 3 hydrogen sulfate. The chromium 3 ion is Cr3+, and the hydrogen sulfate ion is HSO4 2-. So that will result in Cr2 HSO4 in brackets 3. And we can let these subscript numbers lead us in terms of showing us the number that we can expect on the left. So we need 2 Cr3 pluses to balance out 3 HSO4 2-. Again, 2 times 3 gives you 6, and 3 times 2 gives you 6. So we need to make sure that we balance out these superscripted charges. Now, that brings us to the end of ionic bonds, and we can now look at metallic bonding. What is a metallic bond? A metallic bond consists of delocalized electrons that surround a positive metal ion core. Let's take a look at what that means. Most metals are made up of big atoms, so they have a lot of valence electrons. And in a metallic bond, when you have a piece of metal, whether it is made up of one type of metal or made up of a mixture of metals, the metal atoms lose their strong force of attraction to their valence electrons. So their core electrons remain surrounding their nucleus. But the valence electrons lose track of which atom they belong to originally, and they're equally attracted to the nuclei, the positively charged nuclei of all the other nearby metal atoms. And so the metal atom becomes a positive cation because it's made up of a nucleus with its core electrons, but it has lost its valence electrons. So the metal cation becomes positively charged, and the valence electrons turn into a sea of electrons that flow around all these metal cations, not quite sure who they originally belong to. They kind of now belong equally to every positive cation that they pass. So we describe these electrons as delocalized electrons. They've lost their home and they're just floating around freely. So this diagram shows us the electron C model, which indicates what a metallic bond looks like. And remember that a bond is an electrostatic force of attraction between the positive part and the negative part of an atom or atoms. So here we can see a sea of negatively charged electrons that surround these positively charged cations. Because metal cations and electrons have opposite charges, they are attracted to each other, and these electrons are also attracted to other metal cations that they pass. And these electrostatic forces are what we call a metallic bond, and that holds the particles of metals very strongly together. And we call that a metallic network structure. We also understand that a metallic network structure is strong, meaning that metallic bonds are strong, and that's what gives metals their strength. The delocalized electrons also allow metals to conduct electricity well, because what is electricity? Electricity is flowing electrons. And that is all we really need to understand about metallic bonding. And the last thing that we need to cover in this section is the relative atomic mass and the relative formula mass. We may calculate the capital M, whether it's called relative atomic mass or relative formula mass, it is capital M. This is going to be very, very important in stoichiometry later. We don't differentiate later between relative atomic mass and relative formula mass. It's just referred to as molar mass, represented by capital M. But for the purposes of this section, we need to know that covalent molecules have a relative atomic mass and ionic compounds have a relative formula mass, strictly speaking. Either way, the calculation for this capital M over here, whether it's for covalent molecules or for ionic compounds, the calculation is exactly the same. And we use the relative atomic mass values represented on the periodic table. If we go to the periodic table, that capital M we can derive by the number under the element. That is the relative atomic mass. So the capital M of beryllium is 9. The capital M of chlorine is 35.5. The capital M of iodine is 127. So let's work out the relative atomic mass, capital M, of NH3, and the reason I call it the relative atomic mass and not the relative formula mass is because NH3 is made up of nonmetals, therefore it is covalently bonded. Either way, the calculation is the same, and it has to be set out as follows. Capital M is equal to 14 for nitrogen, plus 3 times 1, or you can write plus 1, plus 1, plus 1, and you provide a final answer in simply units. For now, we're going to use units. Later on, when we start doing stoichiometric calculations, we're going to see that it is actually measured in grams per mole. We're going to understand what grams per mole actually means. The relative formula mass of NaCl is as follows. Sodium has an atomic mass of 23, and chlorine has an atomic mass of 35.5. So we simply add them up, and we get 58.5 units. And the reason that it's the relative formula mass is because NaCl is ionically bonded. So now we can try to work out the relative atomic masses or the relative formula masses of different covalent molecules or ionic compounds. And for each one, you just need to state whether you're working out the relative atomic mass, which would apply to covalent molecules, or the relative formula mass, which would apply to ionic compounds. So I want you to work out the following. Now, just by looking at these, this is going to be the relative atomic mass because it's covalent. So is this one. It's covalent. And these three over here are ionic. So you'd be working out the relative formula mass, even though the calculation is done in exactly the same way. The other thing that I want you to note is that NH4OH is ammonium hydroxide, and even though it is only made up of nonmetals, it is still ionically bonded because it is made of the NH4 plus and the OH minus ion. It's one of those exceptions. So for HCN, the relative atomic mass of HCN is capital M is equal to 1 for the hydrogen, 12 for the carbon, and 14 for the nitrogen, and that gives us 27 units. The relative atomic mass of carbon dioxide is 12 for carbon plus 16 because there are 2 oxygen atoms involved in CO2, and that gives us a total of 44 units. The relative formula mass of sodium carbonate, Na2CO3, is 23 plus 23 because there are 2 sodium atoms, plus 12 because there's 1 carbon atom, plus 16 times 3 because there are 3 oxygen atoms. And that gives us an answer of 106 units. NH4OH, we're working out the relative formula mass. So it is 14 plus 4 hydrogens, so 1 times 4, plus 16 for the oxygen, plus another 1 hydrogen. and that gives us an answer of 35 units. And lastly, CuNO32, the relative formula mass is 63.5 for copper. Then we've got NO3, which is made up of nitrogen and 3 oxygens, but we've got 2 of this family group. So we've actually got 2 nitrogens and 6 oxygens, which is why it is 14 times 2 and 16 times 6. The way that you set this out is not important, provided that you represent the correct number of atoms. And the final answer would be 187.5 units. Remember the periodic table that you get given from grade 10 to matric. You're going to use the exact atomic mass values. If a certain element like copper has got a mass of 63.5, we leave the 0.5 as part of our calculation.